Okay, this is the last lecture in the course, and today I want to continue to speak about Matroids and a little bit, hopefully, about the connection to FPT. But first, let's speak a little bit about this really interesting problems about Matroid intersection. So, what is a Matroid intersection? Well, what you would expect. You have Matroids, so let's call it MI. We have the same universe, and then we have the sets, right? So for I equal to k, well, k is not a good choice. Let's call it I don't know, t. And what we're interested in the structure formed by the intersection of the matroid. I think about it as a set system where we take the intersection of the FIs. Right. We are looking on the sets, and we take the intersection, right? And we can look on the set system, and now we can ask natural question about the set system, right? Compute a large set in this set system, and so on, right? To remind you quickly, what is a matroid? A matroid is we have a set, a ground set U, and we have a family of subsets, and we require three properties. The most important, the most important one is hereditary, right? If a set is in the set system in the family, then a subset of it is in, and then we have the exchange property that says that if we have a bigger set that in the matroid than a given set, then there is always a way to add an element to the set such that we increase it and it's still in the matroid, right? This is this way to go up, which means in particular that the maximum size sets in the matroid are all of the same size and they're called bases, right? Okay, so now we are interested in this intersection set system, and of course the most natural thing to say is, oh well, maybe this intersection is a matroid. So the answer, of course, this would be too easy. So observation, intersection of two matroids is not necessarily a matroid. Okay, and this is just you need an example, so I'm just going to form, let's look on a set of 4 points, right? And now I have to tell you what is the ground set. So the ground set are of course going to be the singletons. And then I'm going to take an edge of size 2. Okay, maybe I should improve it now. I take this set of size 2. And then here's the interesting stuff. I'm going to take this triple. And finally, I'm going to take the set that is everything. So this is going to be one matroid, right? The other matroid, and this is clearly a matroid, right? Right, we can always, sorry. So I guess one has to be a bit more careful. So this singleton is not going to be, okay, let's try again. This is going to be this set, and this is going to be this set. And, right, and the important thing is that the fourth element participates only in the largest set, right? So this is clearly a matroid, right? Right, the basis is the 4 points, and we have the exchange property, right? So that's great. So it's a matroid. Oops. Yeah, and in fact the two top elements are not in their own singletons, right? So we don't have a problem with the exchange property with them. Okay, now all I'm going to do is essentially create another Matroid which is a reflection, right? So the triple set is going to be this one. The elements are the same. The four elements are the same in a natural way, right? Okay, so those are the two Matroids, right? I can write them explicitly if you want, but the family set here, so if it's this, you know, if I number them 1, 2, 3, 4, right, then the Matroid on the left is empty set, I guess, 1, 2, 1, 2, and 1, 2, 3, and 1, 2, 3, 4. 1, 2, 3, 4. Right, so this is going to be the Matroid that on the left. The right one is the same essentially, except that let me use a different color. Empty set 1, 2, 1, 2, and now the difference, right? 1, 2, 4, and 1, 2, 3, 4. 1, 2, 3, 4. Okay. So this is the other Matroid, right? This is just a family of sets. Now the important thing to observe is, of course, that the intersection of those two Matroids is equal to the following, right? It has the empty, you know, what of course is happening is that we are going to lose the triple sets because they are different, which means immediately that we get, this is 1, 2, 1, 2, and 1, 2, 3, 4. Okay. And this set is of course not a Matroid because the exchange property fails, right? There is no way to go from this set to this set by adding only one element, right? There is no climbing. So as such, this is not a Matroid. So Matroid intersection sucks. It's not a Matroid. That's the summary. But nevertheless, it turns out that you can compute, you can still solve the natural problems on the intersection of two Matroids, right? Now, unfortunately, so intersection of two Matroid right? So here the problem is the usual thing, right? Is we have M1 and M2. We look at the intersection and we ask, you know, is there an edge? Is there a set in M1 intersection M2 of size at least k? Okay, so this problem, it's not hard, you know, this problem is known to be polynomial. So this is polynomial. Which is nice, but this problem becomes much harder, you know, despite the fact that the Matroid here is not, the intersection is not a Matroid, we can still essentially solve this find largest set problem, which is nice, but it's not very difficult to show that intersection of three Matroids NP-hard. Okay. And the proof is not hard. The trick, the reduction is to Hamiltonian paths of proof. Hold on, it's stated as a claim. So proof is a reduction. So you need reduction from Hamiltonian paths in a bipartite graph. Okay. So it's easy to verify that this problem is a variant of Hamiltonian path that is NP-hard. If you want, you can prove it. It's not hard. It should take a few minutes. But let's just take it on faith. The tiny problem mentioning the word Hamiltonian path is NP-hard. So let G be this graph. Okay, and let's draw it. Right, it has two sides. Right, and we're going to build three Matroids. Right, and the Matroids are going to be on the edges. The first Matroid, so it's a bipartite graph. The first Matroid would contain only sets of edges such that every vertex is contained in at most two edges. Maybe in one edge or no edges, but in at most two edges, right? So this is an example of partition Matroid essentially. I think partition Matroid will allow at most. You have it, upper bound of 2 for every one of those constraints. So let's call it ML. Edges, subsets of edges, such that no vertex on the left is adjacent to three edges. Okay. Okay. And this is clearly a Matroid. Okay. So that's the left Matroid. And we define the right Matroid the same way, right? On right. Collection of edges such that no vertex on the right is adjacent to three or more edges. Right? Okay. So essentially, a valid set that belongs to both Matroids is a set of edges such that every vertex is containing 0, 1, or 2 edges of the set. Right? That would be the intersection. And the third Matroid is just going to be the graphical Matroid. Let's call it MG. The graphical Matroid. So what is the graphical Matroid? To remind you, this is just the Matroid on the edges where a collection of edges of the graph is a valid set in the Matroid, if and only if it does not contain a cycle, right? So you can think about it as a set of all allowable, all forests, right? And now all we need to do is let's look on the intersection, right? So what is the intersection? The intersection is going to be all spanning forests such that the degree of a vertex ML, MR, and MG, the intersection is all forests with max degree 2, right? Because the left Matroid enforces that the left vertices have degree at most 2, the right Matroid forces that all the vertices have degree at most 2, and the graphical Matroid forces the fact that it's a forest, right? So those are all the This contains all the forests that have this constraint. And of course, a Hamiltonian path is just such a forest with n minus 1 edges. So G has Hamiltonian path if and only if the intersection, let's call it I contains a set, well, it's a collection of edges, so a set of n minus 1 edges. So this, as such, solving this, deciding if in the intersection of 3 Matroid there is a set larger than n minus 1, which would be that parameter k mentioned above, is equivalent to Hamiltonian path, which is an NP-hard problem. So Matroid intersection is polynomial for 2 and hard for 3. Okay, let's move on. There is another interesting problem. Maybe interestingly, if you have a Matroid, so this is lemma 12, lemma 12.5, let me just mention it, it's kind of interesting. It says that if it's a Matroid, and we have another Matroid, but it's not such an interesting Matroid, it's a U of R. U of R is the uniform R Matroid. So what is a uniform Matroid? It's just a Matroid that contains all subsets up to size R. You know, it's the simplest thing. Then the intersection is still a Matroid. Right. And it can be converted into a linear Matroid. Right. And you can compute a linear Matroid representing it over a finite field, blah, blah, blah. Okay, so the next problem to talk about is Matroid parity. And at least for me, the easy way to think about it is that I give you a graph. Okay. Vertices and edges, right? And you would like to compute, and I give you a Matroid also. The Matroid is defined over the same set of vertices. Okay, and compute is there a matching T in G such that, you know, we take the union of the vertices UV is in the matching, right? And we take the union of their sets, right? The corresponding set of vertices. This is in the Matroid, right? So this is kind of a generalization, essentially, of maximum matching, right? You essentially have a maximum matching where you have a Matroid constraint, right? That says, you know, you cannot just pick any set of edges that form a matching. Somehow the associated set of vertices needs to be in the Matroid. Okay. So it turns out that this problem is polynomial. I'm not going to show how, because it's in fact non-trivial. There are some very cute by now algebraic algorithms for this. essentially, which took quite a while to figure out. So the idea is somehow that you write down a matrix, and the problem somehow boils down to the rank of this matrix, whether this matrix is full rank or not. So you compute the determinant, you get a polynomial, and now you ask what's the rank of the polynomial, right? And if it says if the polynomial is not zero, then the rank of the matrix is full, and then there is a solution of size k, and oh, I forgot to say that we require that the matching is of size k. Matching of size larger equal than k, right? More at least k edges. Okay, so essentially, once you have this formulation, then checking checking whether the matrix is full ranked or not, can easily be done by this is a polynomial. We have the Lempel-Ziff lemma that says that you can just do you can evaluate the polynomial on a small number of random values to check whether it's zero or not, and you just do that, and you're done. In fact, you need to check only on one value if the field you're working over is large enough. So, and that's it, right? So it's easy to check, and in fact, you can use it then to find the matching, right? Essentially, what you do, you use a greedy algorithm. You remove an edge, and you check whether the remaining graph still have a remaining matching under the constraint of the Matroid. What I skipped here, which is very important, so all this stuff works only if we are dealing with linear Matroids, right? So M is a linear Matroid. To remind you, a linear Matroid is just, I give you a matrix where the elements are columns, and a set is valid if it's the corresponding set of columns is linearly independent in the respective space. So this problem, M is a linear Matroid, so Matroid parity So, as I said, after a clever algebraic reduction, this boils down to essentially, evaluating the determinant, and if you want the set itself, you just need to use some kind of a greedy algorithm. The details are not trivial, and I should say also that people know how to solve it. In general, without matrix multiplication, intuitively, this is going to be with Matroid parity. Okay. So this is roughly equivalent to general matching in graph. Right. So you also matchings in bipartite graph, which are just network flow, but there are a polynomial time algorithm for matchings in general graph, which are much more difficult. You have to do all this blossoms nonsense and so on, at least if you want to avoid matrix multiplication. And essentially the algorithm for Matroid parity essentially can be interpreted as extending this Hungarian method, the blossoms algorithm for this kind of stuff. As I said, there is, from a quick look, there's a non-trivial amount of literature on this stuff, and it's not easy. So I'm not going to go into that, I'm just mentioning it. It's maybe important to mention It's worth mentioning that Matroid parity is in fact NP hard. Matroid parity is NP hard. And the reason for the discrepancy here is that the above Matroid was for linear Matroid, right? Essentially, when we have a very good and nice representation of it, but general Metroids, usually the assumption that all you have is an oracle axis, and then you don't really have an easy solution, right? The intuition is that if I give you the Metroid using only oracle axis, then you're really dealing with a set system that potentially have exponential number of sets, and it's hard to handle it efficiently. So Matroid parity is easily solvable only only if we are in the linear settings. Okay. Okay, another problem is the maximum matching can easily be reduced to Matroid intersection, right? Because just use the NP hardness proof we did, right? You just define a partition Matroid on the left side, right? Every vertex on the left can be engaged at most once. Another Matroid on the right, every vertex can be intersected at most two. So such maximum matching on bipartite graph is immediately the intersection of two is exactly the intersection of two Matroids. Okay. And in fact, one can reduce maximum matching. So maximum matchings in general graph to matching parity. But in fact, I already did that, right? Because the way I stated, I said that the Matroid parity problem slightly different than the book. I presented it as just complete maximum matching with the Matroid constraint. So if you remove the Matroid constraint, you're just going to get maximum matching, right? Matroid parity. Okay, so that's good. Let's see. What do we want to say next?